Danieli is a global leader in supplying advanced equipment and technologies for steel production, ensuring high efficiency, quality, and sustainability. A modern Danieli steel plant integrates sophisticated machinery across every. The twin ladle furnace with two ladle cars enables simultaneous handling of two steel heats, boosting productivity and reducing tap-to-tap times. Each ladle can undergo precise temperature adjustment, alloying, and homogenization. The two ladle cars ensure swift ladle exchanges between the furnace and caster, optimizing workflow and minimizing delays in continuous casting operations. The twin-tank single-cover vacuum degasser features two treatment tanks sharing a single vacuum cover, enabling alternating operation for high productivity. It efficiently removes dissolved gases like hydrogen and nitrogen, improves steel cleanliness, and ensures precise carbon control. The single-cover design reduces cycle times and operational costs. The mechanical dry pump generates vacuum without oil contamination, ensuring clean operation. It offers high reliability, low maintenance, and energy efficiency, crucial for modern vacuum degassing processes. The three-strand caster produces 300, 450, and 500 mm round blooms, ensuring high productivity, dimensional accuracy, and superior internal quality. Danieli power mold equipment uses advanced oscillation and cooling control to optimize solidification in continuous casting, enhancing surface quality, reducing defects, and ensuring consistent bloom dimensions for various steel grades. The mold and final electromagnetic stirrer, FEMS, improves internal steel quality during continuous casting by generating controlled electromagnetic fields that stir molten steel inside the mold and strand. This action reduces segregation, minimizes centerline porosity, and refines the solidification structure. The mold stirrer ensures uniform shell growth and smoother meniscus behavior, reducing surface defects. The final stirrer further homogenizes the solidifying core, ensuring better mechanical properties and higher cleanliness in blooms, essential for demanding applications like high-quality bars or seamless tubes. The walking beam reheating furnace uniformly heats billets or blooms, ensuring precise temperature control, reduced scale formation, and efficient fuel consumption before rolling. The breakdown mill performs initial deformation of cast blooms or billets, reducing their cross-section and shaping them for further rolling. It ensures consistent metallurgical properties, eliminates internal defects, and improves dimensional accuracy. Robust design and precise control allow flexibility for different steel grades and product sizes in downstream processes. The 6SHS Plus mill refines shape and size precision. Danieli Automation Q3 Intelligence Architecture integrates process control, data analytics, and AI, optimizing productivity, quality, energy efficiency, and predictive maintenance in steel plants. The DST, the drawer 4-roll module block, delivers precise bar sizing, achieving tight tolerances down to 1/8 DIN for superior product quality. The high-quality bar line ensures consistent surface finish, tight dimensional tolerances, and superior mechanical properties for demanding industrial applications. The 78 x 16 meters walking beam cooling bed uniformly cools bars, prevents distortion, and gently handles products for straightness and surface quality. As part of a major modernization program, an Austrian steel manufacturer undertook the ambitious task of replacing 3 existing 160-ton converters with larger, state-of-the-art 180-ton converters. This upgrade aimed to increase the plant's annual production capacity from approximately 5.4 million tons to 6 million tons, while also improving operational efficiency and product quality. The project presented significant challenges. The original steel plant, built in the early 1970s, was designed for smaller equipment, so space constraints were tight. Moreover, the replacement work had to be carried out, while the other converters remained in operation, ensuring continuous steel production. Prime Metals Technologies was contracted to execute this complex endeavor. The new converters were manufactured overseas, shipped via waterways, and delivered to the plant in large sections. To minimize production downtime, extensive pre-assembly took place on site. Precise welding, alignment, and rigorous testing ensured the new units met strict engineering standards. Dismantling the old converters was a process involving cutting them into large sections for safe removal. A novel technique was employed to shear off part of the existing foundations using a diamond-studded cable saw, allowing for the construction of reinforced foundations for the new converters. Once installed, the new 180-ton converters featured innovative technologies including a compact and maintenance-free suspension system, improved tilting mechanisms, and advanced alloy additive systems. The first converter replacement was completed in just 45.5 days ahead of schedule, with successful commissioning and rapid ramp-up to full production. First, the CNC automatic beam drilling machine is employed to drill precise holes into steel plates as per the design requirements. This computerized process ensures high accuracy and repeatability. Next, the CNC automatic cutting machine cuts the plates into required dimensions and shapes for the flanges and web sections of the H-beam, minimizing wastage and ensuring clean edges. Following cutting, the CNC automatic punching machine punches additional holes where necessary, maintaining consistency across multiple beams. Meanwhile, prefabricated plates are prepared, often including stiffeners or additional structural components essential for reinforcing the beam's strength. In some cases, when specialized or non-standard holes are needed, the manual punching machine is used for flexibility and custom work. The bandsaw machine then cuts various components, especially where intricate or angled cuts are required for the assembly. Cutting on the mark point is performed to ensure precise dimensions and alignment. Technicians mark reference lines on the plates, which serve as guides for cutting and assembly, ensuring the accuracy of the final product. During fit-up, the cut and prepared components, flanges, web, and stiffeners, are positioned and temporarily fixed together. Skilled technicians ensure correct alignment and dimensions during this stage, using fixtures and clamps to hold the components in place. Welding follows, where the assembled parts are fused to form a rigid structure. High-quality welding techniques, including both automated and manual processes, ensure robust joints and structural integrity. Post-welding, the beams undergo finishing processes, like grinding to smooth weld seams, removing spatter, and ensuring uniform surfaces. The semi-finished H-beams are then transferred through material handling for manual shot blasting, where workers manually prepare the surfaces for coating by removing scale, rust, and contaminants. Manual shop blasting uses abrasive materials propelled against the beam's surface to achieve a clean, rough profile suitable for paint adhesion. Larger volumes of beams often proceed to material handling for automatic shop blasting, where they are loaded into the automatic shop blasting machine. This machine uses high-speed turbines to blast abrasives onto the beam surfaces uniformly, achieving consistent surface preparation with greater efficiency. Finally, the cleaned beams move to the painting primer stage. A protective primer coat is applied to prevent corrosion and enhance the beam's durability during storage, transportation, and installation. The primer also provides a suitable base for any subsequent finishing coats if required by the client's specifications. Throughout this manufacturing process, meticulous quality control ensures that each H-beam meets the relevant engineering standards and customer requirements. The result is a high-strength, precisely fabricated steel beam ready to serve as a vital structural element in construction and industrial projects worldwide. The BOST series from Bosdemir represents a robust solution for cable manufacturing with its high-performance rigid stranding lines. Designed to deliver precision, efficiency, and reliability, these machines cater to the production needs of cables using copper, aluminum, or empty reels, supporting a wide range of industrial applications. One of the defining features of the BOST series is its compatibility with connectable rigid cages that accommodate reel diameters of E560mm and E630mm. This flexibility allows manufacturers to optimize their operations for different cable dimensions and materials, enhancing productivity and reducing downtime for changeovers. Advanced engineering is evident in the system's key features. The motor-controlled pintle movement ensures smooth and precise handling of reels during loading and operation, while the pintle activation control adds another layer of operational safety and convenience. A practical loading system simplifies reel handling, minimizing manual intervention and improving overall efficiency. The gearbox-driven system ensures consistent torque and reliable performance even under demanding production conditions. The BOST series offers impressive rotational speeds depending on the number of strands and material type. For 6-unit configurations, speeds reach up to 220 revolutions per minute for copper, 310 revolutions per minute for aluminum, and 340 revolutions per minute when empty. In 12-unit cages, the line operates at 180 revolutions per minute for copper, 275 revolutions per minute for aluminum, and 320 revolutions per minute empty. For 18-unit lines, speeds are 160 revolutions per minute, copper, 245 revolutions per minute aluminum, and 285 revolutions per minute empty. In 24-unit configurations, the machine maintains 130 revolutions per minute with copper, 205 revolutions per minute with aluminum, and 230 revolutions per minute empty. These figures reflect the machine's capability to balance speed with precision, ensuring consistent strand quality across a variety of production setups. The manufacturing process begins with the procurement of high-purity raw materials from reputed suppliers. Rigorous mechanical and electrical tests are conducted on all incoming materials to ensure they meet stringent quality standards before production. A critical step is wire drawing, where thick copper or aluminum rods, typically 8 mm in diameter, are reduced to finer diameters, sometimes down to 1.6 mm. This reduction is achieved through successive dies that stretch and thin the wire while maintaining precise tensile strength, resistance, and dimensional accuracy. Once drawn, the wires undergo stranding, where multiple wires are twisted together to form conductors as per design specifications. High-speed stranding machines ensure consistent conductor formation, and the compacting process minimizes air gaps, reducing AC losses and enhancing electrical performance. The Sakura X-section monitor imported from Germany is a highly advanced online measurement system used during the cable installation process at Havells Alwar plant. Installed directly on the extrusion line, it continuously scans the cross-sectional geometry of the insulated wire using sophisticated laser or X-ray technology. It precisely measures parameters such as insulation thickness, concentricity, and diameter in real time. This enables immediate detection of any deviations or irregularities, ensuring uniform insulation without defects like air gaps or thin spots. The system provides visual feedback and digital records, allowing operators to make quick adjustments and maintain tight production tolerances. This rigorous control significantly improves product quality, electrical performance, and safety standards of Havells cables and wires. Following laying up, cables receive an inner PVC sheath using computerized extrusion lines. Havells is distinctive in manufacturing its own PVC in-house rather than sourcing it externally. This practice ensures better quality control and improved flame retardant properties. The extruded inner sheath not only maintains the circular shape of twisted cores, but also acts as an additional moisture barrier, protecting insulation in the event of outer sheath damage. In the armoring stage, cables are reinforced based on application requirements. Single-core cables are armored with aluminum or aluminum alloy strips, while multi-core cables use steel wires or strips. The armor is coated uniformly with zinc, ensuring rust resistance and mechanical protection against external impacts. The cables are then covered with an outer PVC sheath using advanced sheathing machines. Again, Havells' in-house PVC production provides significant advantages in quality and flame retardant performance. Quality assurance is stringent. Havells' in-house lab, accredited by NABL and recognized by DSIR, conducts over 30 tests on physical, mechanical, electrical, thermal, chemical, and fire properties to ensure product reliability and safety. OXY-FUEL cutting, often known simply as flame cutting, is a versatile and cost-effective process used to cut ferrous metals, especially carbon steel. When combined with modern CNC computer numerical control technology, it can achieve precise and high-quality cuts suitable for a wide range of industrial applications. Although some people associate OXY-FUEL cutting with rough edges or less precise finishes compared to methods like laser or plasma cutting, advancements in equipment and cutting techniques have significantly improved the quality of results. CNC-controlled OXY-FUEL machines deliver accurate cuts with clean edges and minimal dross, even on thicker materials where other cutting methods might struggle or become cost-prohibitive. A great example of high-quality CNC OXY-FUEL cutting is seen in parts made from 6 mm thick carbon steel sheets. This thickness is well within the ideal range for OXY-FUEL cutting, allowing operators to produce components with excellent edge quality, consistent dimensions, and minimal heat distortion. The process works by directing a high-temperature flame onto the metal surface, followed by a stream of pure oxygen that rapidly oxidizes and blows away the molten metal, creating a clean cut line. Beyond just cutting, CNC OXY-FUEL systems offer automation, repeatability, and the ability to execute complex shapes and patterns directly from digital designs. This makes them invaluable in industries such as construction, shipbuilding, heavy machinery manufacturing, and metal fabrication shops where precision and efficiency are critical. Threading a 3/4 diameter, A36 steel rod with 10 UNC, Unified National Coarse, threads per inch using a tangential threading machine is a precise machining process requiring proper setup and cutting parameters. A36 steel, a low-carbon structural steel, offers good machinability, but considerations like cutting speed, tool geometry, and lubrication remain crucial to achieve clean threads and prolong tool life. With the machine set to 126 revolutions per minute, RPM, the tangential threading head engages the rod tangentially rather than radially, minimizing deflection and vibration, which is advantageous for producing consistent, high-quality threads. The tangential tool holders allow multiple threading inserts to cut simultaneously, distributing cutting forces and reducing tool wear. For 10 TPI on a 3/4 rod, the pitch is 0.1 inch, requiring precise tool positioning and feed control to maintain accurate thread depth and pitch diameter. Coolant application is recommended, especially at 126 revolutions per minute, to dissipate heat, improve surface finish, and prevent galling of the steel. Before threading, the rod's diameter should be verified to ensure it's within tolerance, as oversized stock can produce undersized thread roots. The cutting tool geometry should match the UNC thread profile, typically a 60-degree thread angle, with proper relief angles to avoid rubbing and excessive heat buildup.